There's now a particle P of mass 6 kilograms that lies on a rough plane inclined at an acute angle theta to the horizontal. We know the mass, it's a rough plane. There's a horizontal force of 12 Newton that's acting. Coefficient of friction is mu. Okay. P is in equilibrium. That means opposite forces are going to be equal to each other. It's on the point of sliding down the plane. That's limiting equilibrium. F equals mu r. Show that mu equals this. All we have to do is, they have told us it's equilibrium, limiting equilibrium, equate the opposite forces. Let's represent all the forces. First of all, P has a weight of 60 Newton that acts vertically downwards. There will be normal reaction. It acts in this direction. P is on the point of sliding down. If it's on the point of sliding down, friction opposes that, and that acts up the plane. There's this force 12 Newton acting to the right side. I always recommend the direction in which the force is acting, you should represent that force on that side. So where is 12 Newton acting? It's acting to the right side. Remove it from here, represent it on the right like this. That will make it easier for you to understand how you're going to resolve this force. So 12 is acting to the right. Let's represent it here. Is there any other force acting? We have represented weight, friction, reaction, and that's it. Okay, these are the forces. Now let's resolve them. When we have a surface involved, we normally resolve parallel to and perpendicular to the surface like this in these directions. Let's resolve weight. This is 60 Newton. One component of weight is going to act in this direction. This angle is theta. The component adjacent to the angle, that is going to be 60 cos theta. The component on the other side, that's going to be 60 sine theta. 12 Newton is acting in this direction. What about the components of 12? 12 is going to have one component acting in this direction, another component acting in this direction. If this angle is theta, this is alternate angle. This is corresponding angle, theta. So this component is going to be 12 cos theta and the other one is going to be 12 sine theta. So we resolve the forces like this, equate opposite forces, 12 cos theta, F, and 60 sine theta. These are the forces acting along the surface. Or 12 sine theta, 60 cos theta. These are the forces acting perpendicular to the surface. Equate the opposite forces and you should be able to get that somehow. Let me know if there's any confusion in resolving forces here. Is this clear to everyone? The way we're resolving the forces? Yeah, okay. All right. Let's just equate the opposite forces then. Left equals right, up equals down. Why are we doing this? Because this is equilibrium. We don't always do this. We only do this when we have equilibrium. We equate the opposite forces like this. Okay, to the left, we've got 60 sine 30. To the right, we have F plus 12 cos theta. Then up equals down. That means R equals 12 sine theta plus 60 cos theta. This is what we end up getting. They want us to show that mu is equal to this. What you can do is you can replace F with mu r first of all. We don't really have enough space for this. F is mu r plus 12 cos theta. That equals 60 sine theta. R is equal to this. Let's input this in the other equation, and that becomes 60 sine theta equal to mu into 12 sine theta plus 60 cos theta plus 12 cos theta outside. We need to make mu the subject. That's what they have here. How do we make mu the subject now? Let's take everything else to the other side. This to the other side. That will become 60 sine theta minus 12 cos theta equals mu into 12 sine theta plus 60 cos theta. Now, let's stop here for a moment. What is it that they want at the end? What is it that they want at the end? They want something in terms of tan. We have sine and cos. Let's convert it to tan right now before we convert it to a fraction, because that will become more complicated then. Can we convert it to tan somehow? We can divide the whole equation by cos theta, divide all terms by cos theta, divide each term by cos theta on both sides. What do we get from that? On the left side, we get 60 tan theta minus 12. On the right, we get mu into 12 tan theta plus 60. Now we can divide this on the other side, and that gives us mu equal to 60 tan theta minus 12 divided by 12 tan theta plus 60. Let's rearrange this. They have the constant written first here. I'll just write it like that. 60 plus 12 tan theta. We can take 12 common from both the numerator and the denominator. So we're left with 5 tan theta minus 1. In the denominator, we have 12 into 5 plus tan theta. Okay, and then finally mu turns out to be 5 tan theta minus 1 divided by 5 plus tan theta. That is what we had to show. Mu is equal to this. Is that okay? These were actually not as difficult as they looked initially. Only question number 5 was a bit tricky. Let's look at the last one now. Hence, find the set of possible values of theta. Find the set of possible values of theta. Do they have any information here? Particle P of mass, this. Which hence means we have to use the previous part somehow. In the previous part, we have proved that mu is equal to 5 tan theta minus 1 divided by 5 plus tan theta. Set of possible values of theta, so we need some kind of an inequality. Is there anything that we can say about mu that we have found in the first part? Line of action is this, 12 Newton passes, coefficient of friction is this, P is in equilibrium on the point side, now the plane. Tan theta is greater than 0. Why tan theta is greater than 0? That is, you can say theta is an acute angle, yes. That's all that tells you, that it's an acute angle. But is that the only restriction that we've got? We have to use the previous part somehow. In the previous part, we have found the value for mu. Is there any restriction on coefficient of friction? Coefficient of friction, what can be the values of coefficient of friction? Coefficient of friction, what can be possible values of coefficient of friction? Coefficient of friction has to be a positive number always, right? It can't be equal to 0, because that would mean it's a smooth surface. This is a rough surface. So it has to be some positive value. Negative is also not possible because coefficient is always a positive value. That is one thing that you could do. You could say mu is greater than 0, and that gives you 5 tan theta minus 1 divided by 5 plus tan theta greater than 0. This goes to the other side, gets eliminated, and we're left with 5 tan theta minus 1 greater than 0. Tan theta greater than 1 over 5. Now, since theta is acute, we know that we are in the first quadrant in which tan is positive. We could take tan inverse on the other side, and theta will be greater than tan inverse of 1 over 5. You can see what that value is in degrees. Did they say tan is in degrees, or theta, plus values of theta? They just said theta and did not mention if it's degrees or radians. You can see what this value turns out to be. What do we get from this? Tan inverse of this? 11.3 degrees. Theta should be greater than 11.3 degrees. And of course, it's an acute angle, so it should be less than 90 as well. That's a weird question though, but that's the only thing that you can do based on the first part. You found that mu is equal to this, right? They said, hence, find the set of possible values of P, possible values of theta. So what could be a possible condition for mu? There's nothing additional to this that the question mentions. So you could say mu is supposed to be a positive number because it's a rough surface. So we put this greater than 0. Why is theta greater than 0? Mu greater than 0, right? Mu greater than 0 because it's a rough surface, right? It's a rough surface. Mu tells you the roughness of the surface. How much a surface is rough, it quantifies that number. So if it's a rough surface, it has to be some value greater than 0. For a smooth surface, mu is equal to 0. No problem in this one. I think let's do this, yeah. Let's do question number 7, because this actually does look slightly complicated. The second part of this, not the first part. The rest were fairly straightforward. In fact, the first one as well, it's that idea we use limiting equilibrium cases. Let's do this one. Two particles A and B of masses 6.5 kilograms and m kilograms respectively. They are connected by a light inextensible string that passes over a smooth pulley. The pulley is fixed at the top of a rough plane, which is at an angle alpha to the horizontal ground. Okay, all of that information is there on the diagram. It's a rough slope. Tan alpha is 5 over 12. That's another important piece of information. Coefficient of friction is 0.4. Now, given that the system is in equilibrium, find the set of possible values of m. Now, if they say the system is in equilibrium, find the set of possible values of m. What does that mean? We're looking for the maximum possible value of m, the minimum possible value of m, and then anything between them is also going to be possible, right? So in such cases, what we do is we take the two extreme cases of equilibrium. Two extreme cases of equilibrium. One extreme case would be that the object B is just about to go down and A is just about to move up the slope. And the other extreme case would be that A is just about to move down the slope and B is just about to move up. Right? You consider these two extreme cases of equilibrium. You'll get a value for M for each of them. And then any value of M between those two values, that is what is going to be the set of possible values of M that we're looking for. Okay, that's a standard point, but that's the idea that we use in this. Make two cases, case 1, case 2. Case 1 is when, let's suppose, A or B is just about to move down, or A is about to move up. Just use A because friction has to do with that. A about to slide up. That's case 1. And then the second case would be A is just about to slide down. That will be the second case. Now, what changes in both of these cases? The direction of friction. Direction of friction changes in both of these cases, right? Now, if A is about to slide up, let's represent all the forces acting on both the particles. At B, we've got weight acting downwards, tension acting in the upwards direction. At A, we've got tension acting upwards, weight acting vertically downwards, which is 65 Newton. There will be two components of weight, one in this direction, one parallel to the slope, along the slope. If this angle is alpha, then this angle is also alpha. This component is 65 cos alpha and the other component is going to be 65 sine alpha. There's going to be normal reaction in this direction. And if A is just about to move up the slope, then where does friction act? Friction acts down the slope. So if A is about to slide up, what that means is friction is going to oppose that acts in this direction. Now, it's limiting equilibrium. It's limiting equilibrium. So F is equal to mu r, just equate opposite forces. For B, you can say T equals 10m, right? From when you equate opposite forces for B. So T is equal to 12, 10m, that's not changing in both of those cases. And we can also say for A, R is going to equal 65 cos alpha, that's also not changing. So that will be common to both of them. R is going to equal 65 cos alpha as well. Forces along the plane, they are going to change. This is T, this is 65 sine alpha, this is friction. In the first case, friction acts in the downward direction, so the equation would become T equal to 65 sine alpha plus F. Okay. In the second case, when we say it's about to slide up, sorry, in the second case, I have to change that. When it's about to slide down in the second case now, in that case, all that changes is the direction of friction. Friction will now act up the plane. So in the second case, friction acts up the plane. What will be the equation in that case? In that case, the equation is going to become T plus F equal to 65 sine alpha. These are the two equations that we end up getting. F will be the same in both cases, yes, because mu is the same, R is the same. So the value for F is going to remain the same, yes. Now let's find cos alpha and sine alpha. They don't want exact values. That means you can just input them in the calculator. You don't necessarily need to use a right angle triangle. 5 over 12, that's perpendicular over base. Perpendicular is 5. So it will be 5 over 13 and cos alpha is going to be 12 over 13. You can just put them on your calculator. Your calculator will give them to you. Sine alpha is 5 over 3, cos alpha is 12 over 13. Now we just solve these equations. Tension, remember, is equal to 10m. Let's replace it with that. 10m equals 65 sine alpha. Sine alpha is 5 over 13 plus F. F is mu times R. Let's simplify this further. 10m equals 25 plus mu, which is 0.4. Let's just simplify this here a bit. R equals 65 into cos alpha, which is 12 over 13. That will be 12 into 5, which is 60. So the value of R is 60. That's going to be the same for both cases. So it becomes 0.4 into 60. And that will give you one value for M. You can see what that is. In the second case as well, T is equal to 10M plus F is mu R. That equals 65 sine alpha. Sine alpha is 5 over 13. 10M plus 0.4 into 60. That equals 25. And that will give you another value for M. You can see what they are. What's the first value of M and the second value of M? 25 plus 0.4 into 60 divided by 10, that's 4.9, right? Somebody please confirm this as well. In the second case, 25 minus 0.4 into 60 divided by 10, that's 0.1. These are two extreme values of M that we're getting. These are two extreme values of M that we're getting. If it's equilibrium, we considered the extreme cases of equilibrium, that what happens if A is about to slide up the plane, and the other extreme case, if A is about to slide down the plane. That gave us two extreme values of M. So what are all the possible values of M then? Between these two numbers, write the smaller number on the left side, bigger number on the right side with less than signs. M is between 0.1 and 4.9. That's the final set of values of M for which the system is in equilibrium. That's 7 marks. This is all that you had to do in this. All right. Let's look at the next one now. A block of mass 12 kilograms is placed on a rough plane. Now, this looks like a standard question. We have this mass 12 kilograms. Its weight, therefore, is going to be 120 Newton. It's inclined at an angle of alpha, where tan inverse is 0.5, where alpha is tan inverse of 0.5. That's given. It's a rough plane, so there's friction. There's a force of x Newton applied to the block. Coefficient of friction is mu. Okay. Let's look at part B now. Now they're saying it's given instead. When they say it's given instead, what that means is whatever was given in the first part, that is not relevant anymore. So information inside the first part, mu equal to this, x equal to this, that is no longer applicable. So you cannot use any of that information now. Now x is equal to 10 and the block is on the point of moving down the plane. What does that tell you? Limiting equilibrium, right? This is limiting equilibrium. So it's a case of equilibrium now. Find the value of mu and the value of x for which the block is on the point of moving up the plane. Okay, now using this first piece of information first, let's figure out the value for mu in this case. What are the forces that are acting? We already represented the forces that are acting, right? We could just equate the opposite forces. We could say equate forces acting towards right, towards left to forces acting towards right, and similarly upwards forces to downward forces. Now, if you think about it, there's nothing that has changed in this direction. So the value for r that we found in the first part, that is still relevant, right? Because nothing has changed in this case. So r is still the same. The r value, sometimes r can change as well, right? And for one part, it will be one value, and then in the next part, it'll be some other value. So you have to be careful about that. In case it changes, you have to calculate it again. But in this case, it remains the same, and its value was 107.33. Let me just write that down here. Now, let's look at the first case. The first case is it's on the point of sliding down. If it's on the point of sliding down, what are the forces going to be? On the left side, we have 120 sine alpha, and friction still acts in the upwards direction. And these forces will be equal to each other. We would say 120 sine alpha, that should equal x plus f. Now, sine alpha, we already know what its value is. We found that above. 0.44721, 0.44721. X in this part they're saying is equal to 10 plus friction. Friction is at its maximum value, which is mu times r. The value of r is 107.33. And that will give you a value for mu. You can see what that is. That's the first case when the object is on the point of moving down. Okay? That's the value of mu that we're getting. What's the value of mu that we're getting? Can somebody please tell me? This is case 1, about to move down. Once we have that value for mu, now mu represents coefficient of friction. So that's not going to change anymore, right? 0.4068, and then you round it off to 0.407. That's your final answer for mu. Now they're saying find the value of x for which the block is on the point of moving up the plane. So now the second case is it's just about to move in the upwards direction. Now, if it's just about to move, it is still limiting equilibrium. F is equal to mu r. The only thing that changes is if it's about to move in the upwards direction, friction is going to act in the downward direction now. So the direction of friction changes, right? So all we have to do now is use the same equation as before. Just write F on the other side now. Just write F on the other side. So now we have f plus 120 sine alpha equal to this. What we're looking for is the value of x now. F is equal to mu r. Mu is 0.4068. Use the more accurate number into r, which was 107.33. Plus 120 sine alpha, 120 into 0.44721. That equals x. And that will give you the value for x. You can see what that is. 97.3. That's your final answer. This is what we were looking for. ठीक है. अच्छा, coplanar forces of magnitude 16 Newton and 12 Newton, 16, 12, 24, and 8 Newton act at a point in the diagrams, in the direction shown in the diagram. Find the magnitude and direction of the single additional force acting at the same point, which will produce equilibrium. Achha, I'm just going to give you a hint about this. It's not that difficult. It's not hard. It's probably just a confusion with uh, the question statement. You got four forces. They will have some resultant. Okay? Let's suppose the resultant of these forces. Okay, so anyone who has done this, can you tell me what the resultant force is and what the direction of that resultant force is?
सर 23.1 रिजल्टेंट है इसका
Okay,
और
so
ये
resultant that you're getting is 23.1 Newton.
जी सर और जो डायरेक्शन है वो अबव पॉजिटिव अबव नेगेटिव एक्सिस
Above negative x-axis?
जी सर
Okay.
मेरा बिलो आ रहा था तो मेरा गलत आ गया
रिजल्टेंट की डायरेक्शन पूछ रहा हूँ मैं, रिजल्टेंट की डायरेक्शन. जो आपका रिजल्टेंट आ रहा है वो क्या आ रहा है ये बताएं.
हाँ सर यही आ रहा है 3.98 बिल अबव नेगेटिव एक्सिस
That doesn't look like it. फोर्सेस को देखकर doesn't look कि वो रिजल्टेंट होगा. 3.99 degrees below positive x-axis. It's clear that forces acting towards right side are greater, right? So resultant should be to the right somewhere. And downward forces are greater as well. So resultant should be somewhere in this direction, most likely. So you're saying it's 3.97 degrees, 986 degrees, or I can say 4.0 degrees below positive x-axis. When you find the resultant of these forces, it turns out to be 23.1 Newton at 4 degrees below positive x-axis. Now, resultant force you can all calculate, right? Resolve all forces, find horizontal resultant, find vertical resultant, overall resultant, and find the angle, right? Can all of you do that? Right? The standard. They're not asking you for resultant. They're not asking for resultant. That's not the final answer. Just focus on this for now. You will find the resultant force. You'll find the resultant force. This is what the resultant force turns out to be. Okay? Now, पहले सुन लें, we will talk about the marking scheme. Just focus on this. Resultant force is 23.1 Newton at 4 degrees, or you can say 3.99 degrees. 4 is also fine because the instruction is one decimal place for angles in degrees. It rounds off to 4.0. This is fine. Below positive x-axis. So resultant is turning out to be in this direction. The overall resultant of all the forces, that are there, that is in this direction. Theta is 4 degrees. Now they are saying, find magnitude and direction of the single additional force that will produce equilibrium. Currently, the forces that you have on this diagram, there is a resultant force acting in this direction. There is a resultant in this direction. So because of this resultant, the particle whatever that is that a particle or a point? It's a point. So this particle has a resultant force acting in this direction. Okay. If we want to have equilibrium, what is equilibrium? When the resultant of all forces is equal to zero. That is what equilibrium is. When the resultant is equal to zero. How can we make the resultant zero? Where do we put this additional force such that the resultant becomes zero? We put that force opposite to the resultant in this direction, exactly opposite. Same magnitude, opposite to the resultant, 23.1 Newton at that same angle, 4.0 degrees. This force, if we add it to the set of forces, it is going to produce equilibrium. Okay, it's going to produce equilibrium. Is that okay? So you find the resultant. To get equilibrium, you just need an equal force in the opposite direction to that. So that that resultant is balanced and the object will be in equilibrium then. Is that okay? So this is the resultant force. The force that they're talking about then, the additional force that you need to add there, that is 23.1 Newton at 4 degrees above negative x-axis. That will be your final answer. So you have to do all of this working for finding resultant first of all, and then just write down that the additional force has to be exactly opposite of that in this direction.